Welcome again. So in the last lecture, we had summarized the procedure of the matrix force method for indeterminate structures. Today we are going to solve some examples. We'll solve one truss type structure and one frame type structure.
Let us now solve an example to further strengthen our learning of the procedure. So essentially here we are choosing a single bay, single story portal frame, and this is acted on by a force in the horizontal direction. So as the first step, now we begin with numbering of the members. We have numbered 1, 2 and 3, and then after this step, the next step is to identify all the internal forces. So we have two internal forces for each member, and these are basically F1 and F2, and then the superscript basically carries the member number. So we have a total of 6 internal forces, so we label each one of them for clarity on the structure itself. So please note that all the forces which are internal, they are shown with dashed lines, and the ones which are external, they are solid lines. So now we can also form the collective flexibility matrix, because there are 3 members, so the size of the collective flexibility matrix will be 6 by 6, and this also matches well with the fact that there are 6 internal forces. So this expression can be directly written, since this is standard. All the 3 members, they have same length and same EI value, so L by 6 EI is common, and we can now substitute here the values 2, 2, minus 1, minus 1, and we can repeat these along the diagonal. That will give us the collective flexibility matrix. The remaining terms are zeros. As the next step, we have to convert the structure into a primary structure. So since this structure has degree of indeterminacy equal to 3, so we have to choose 3 redundants. So here we are choosing the 3 redundants as the reactions at the right support. Now the choice of the redundants is dependent on the person who is solving. Different persons may choose different redundants, but finally a stable structure should result. So here we now need to obtain the matrix B. So because we have 1 external force and 3 redundants, and the total size of the internal force vector is 6, so our B matrix will be equal to 6 by 4. Now this has to be split into two components, BP and BX. Since there is only one member in the vector B and 3 in vector X, BP will be 6 by 1 and BX will be 6 by 3. So let us now form
the B matrix
using the procedure that will be applying unit forces along all the points of the external forces and the redundants one by one, and by this manner we will be obtaining
the B matrix
column by column. To make the things easier for us, it's a good idea to list along the columns of the B matrix the various internal forces each row corresponds to, because once we form the structure with unit loads applied, and once we get the internal forces for this structure, it will be very easy to fill up the corresponding rows and we'll be able to get the particular column of the B matrix easily. As part of the procedure, we now consider the primary structure to be acted on by a unit force P equal to 1, and under this condition we can obtain the various internal forces, and these are shown here in this figure. So only the left vertical column will have the bending moments and all other members will not have any bending moment in them. So these being determinate structure, we can very easily obtain the internal bending moments at key locations by using equilibrium of either the left part or the right part. So we have obtained the forces and these can be listed along the first column because this is by definition
the first column of the B matrix.
Similarly, to obtain the remaining columns of the B matrix, which are now corresponding to the redundant forces x1, x2 and x3, we apply one by one the unit redundant forces x1, x2 and x3 and find out all the internal forces. Here we are applying x1 equal to 1. So as a result of the peculiar situation, there won't be any bending moment at the left reaction point. Only a horizontal force would be there. This can be ascertained by simple equilibrium, and then the internal forces at various locations can be obtained by simple inspection or considering a section of the structure, either the left half or the right half, and then we can arrange all these forces along the second column. So this is the second column of the B matrix and first column of the matrix Bx. Then we can apply x2 equal to 1 and get the second column of Bx, and finally x3 equal to 1 and we can get the third column of Bx. Now with the available information, we can easily form FPP, FPX and FXX. And then we can obtain the unknown redundants X, because here the support segments are 0. So X vector can be easily obtained as the product of Fxx inverse with minus sign, Fxp and P. Then the internal forces, they can also be obtained by making use of the force transformation matrix PP and Bx. So each has to be multiplied with the corresponding vector either P or X as shown here. After X has been obtained, we can then also obtain the unknown displacements UP by FPP into P and FPX into X. So with this procedure we can obtain the complete solution. So you can do this as a homework and obtain the final answer in the form of the displacements. Let us study another example, and this time we will try to solve an indeterminate truss. Now we begin with the truss we have already solved before, but we convert it into an indeterminate truss by adding an additional member. The truss is acted on by same loads P1 and P2, and we are adding one bottom chord member. So now if we try to check the indeterminacy of the structure, we find that the degree of static indeterminacy is now 1 because of the new member. So here it should be noted that this is indeterminacy with respect to the internal forces. As far as the external reactions are concerned, still the truss as a rigid body would be determinate, because there are only 3 external reactions which can be determined by the 3 equilibrium equations. But here it is indeterminate with respect to the internal forces. Hence, we cannot choose an external reaction as the redundant. Redundant must be chosen among the internal forces only. So what we do, we choose the internal force in the newly added member as the redundant. So what we have done, we have cut this member so that to make the structure a primary structure, and we are showing the forces in this member. We are just zooming up and we are showing the 2 points at the cut portion, and we are showing the forces. Now we are showing these here in the exaggerated manner, but both the points where the pair of forces X are shown, they are one and the same. Just for the sake of clarity, they are shown one on the top of the other. So now we mark up the members. We mark as before 1, 2, 3, 4, 5 and we add the sixth member additional. So now first step is we find FC. So FC will have one additional term, that is for the member 6, and rest of the terms will be exactly same. So the size of the FC will now be 6 by 6 because there are 6 members now. So we have taken L by EA common, so it will be diagonal terms like 1 and root 2 for members 4 and 5, which are diagonal members, braces, the term will be root 2, and for the new member the term will be 1. So this is now FC. Rest of the terms are all zeros. So then the next step is to determine the matrix B. Now the size of the B matrix would be 6 by 3 now. Earlier the size was 5 by 2 because there are 2 external forces. Now instead of 2 we have 3 because a redundant has been added, and the size in terms of the rows has also increased to 6 because of the new member. So this is our B matrix. So we partition it into BP and BX. So BP is the part consisting of the two loads P1 and P2, and BX for X. So all we have to do is one by one we apply the forces P1 equal to 1, P2 equal to 1 and X equal to 1. We have also marked up the rows according to the internal forces. So the first two columns we need not do extra effort, we have already determined. Only thing is that we have to now fill up the entries for member number 6, and for these two cases the entry will be 0 because this is a cut portion. So when we are applying the forces P1 equal to 1, P2 equal to 2, because of the cut there won't be any force in member 6, so zeros are coming here. Next, to obtain the third column, we apply x equal to 1. So this part we are analyzing. Rest we have not done the analysis because it was already there, and you can go through the corresponding example 1. So now we apply a pair of unit forces. So these pair, they are like a system of self-equilibrating forces. So as a result of these, there won't be any external reaction. So all the forces would be generated would be internal forces. The structure is now determinate. So by going through the equilibrium joint by joint, we can determine all the internal forces. So we begin with the left support. So here the force in the diagonal bracing member is compressive force equal to root 2 newtons, and then once we have this, so going by the equilibrium, we can find out forces in all other members. So what we find, the two diagonal braces have compressive force equal to root 2, and all the other members, the vertical members and the top horizontal member, have a tensile force equal to 1 newton. So with this we can fill up all the members of the B matrix. We have also marked up here the members 1, 2, 3, 4, 5 and 6. So one by one we keep filling the entries. So now we have complete B matrix with us. So remember that for the case of compression we are using minus sign. Now what will be the compatibility condition? Here we have the two cut points of member number 6. So when we are applying the forces P1 and P2, the two cut points, they undergo some relative displacement. And similarly, when we apply the redundant force X, they again undergo some displacement. So finally these two cut points are one and the same. So the compatibility condition is that the relative displacement between the two cut points, which is ux, should be 0. So this is our compatibility condition, and based on this condition we can obtain x directly as shown, and after this we can obtain up also. So all you have to do is now get all these matrices FPP, FPX and FXX, and using the already elaborate procedure obtain the redundant x, then up, and then you obtain the internal forces F. So this is your homework. Let us do one more example involving a frame. So here we have a portal frame. The top horizontal member is double the length of the vertical member, and there is a roller at the end, and the horizontal member is under a load UDL W. The lengths are shown as 5 meters and the UDL is 10 kilonewton per meter. Now we are specifically interested in obtaining the displacement at the midpoint of the top beam. Hence, we must consider this as a joint, and there must be some force acting at this point. Only then we will be able to obtain the displacement, because here the governing objects are the forces. Now we also work out the indeterminacy of the system by using the formula for the case of the frames. So this comes out to be 1. Now how we choose this redundant is our choice. This time we will choose an internal force as the redundant, though it's not must. But for the purpose of illustrating, we are choosing an internal force as redundant, as will be shown in the forthcoming steps. So we now break down the structure. The first part, what we do, we have to convert the UDL into equivalent joint forces. So this is our structure A, where we lock the joints so that we get the fixed ended forces, just as we had done in the case of the stiffness approach also. Now remember that for the top beam we have not locked the right end. So we get the reactions for the two parts, WL by 2, WL by 2 vertical reactions, and the moment reactions WL square by 12. For the other part, which has hinge on the right hand side, we get the moment reaction as WL square by 8, and the corresponding vertical
forces
will be 5 by 8 WL and 3 by 8 WL. Then we apply equal and opposite of these forces on case B, so that now when we superimpose A and B, we get the original structure. So these are the now forces acting on the structure, that is B. So we have to analyze B and then we'll superimpose the results of A. Now this also can be broken down into two parts so as to further simplify. So we have two forces like this WL by 2 and then another force 3 by 8 WL. Now what is the effect of these two forces? For these two forces we need not do a rigorous analysis. This we call as B1, because we can obtain the results for these two forces by inspection only, that the vertical member will be under a compression force WL by 2 and the reaction at the left support will be WL by 2 and the reaction at the right support will be 3 by 8 WL. No other force will be there in any other member. So the results for B1 are also known. So A and B1 we have the results, the internal forces and the reactions, and we just analyze now case B2 with just 3 forces, so that helps us in reducing the flexibility matrix size. So we have the forces, we designate these forces. This is WL square by 12, this is WL square by 24, and then the vertical force at the midpoint of the top member is 9 by 8 WL. So we designate these forces as P1, P2, P3. So 9 by 8 WL is P1, WL square by 24 is P2, and WL square by 12 is P3. So here the positive directions are the directions in which these forces are applied. Nothing to do with the sign convention that clockwise or anti-clockwise are towards positive X or positive Y to be taken positive. So the positive directions are purely governed by the directions of these forces. Now the next question is, how do we choose redundant? I am deliberately choosing an internal force as redundant for the purpose of illustration. Otherwise, we have solved one example before where we had chosen external reaction as the Now for a frame, choosing an internal force as reaction, we would have to little bit come out of our comfort zone, but we'll do that for the purpose of illustration. So now we are showing all the forces and the corresponding displacements. So the corresponding displacements are u1, u2, u3, so that we should be able to get at the end. And we mark up the members 1, 2 and 3. The vertical member is 1. The two horizontal members are 2 and 3. So now we can form FC. So FC is a straightforward now. All the members have same flexibility matrix. The size of FCC will be 6 by 6 because there are 3 members. So you can form FC yourself. Now we just mark up the internal forces. We have 3 members, so it's always good idea to mark up these because this gives us clarity at the time of forming the B matrix. So we have 6 internal forces. So F1 and F2 for member number 1, F1 and F2 for member number 2, F1 and F2 for member number 3. So the member number is labeled in the superscript. So remember, the forces which are the truly external, they are shown with solid lines. So the size of the B matrix, because there are 6 internal forces, so the rows will be 6, and since there are 3 externally applied forces and 1 redundant, the columns will be 4. So the size of the B matrix is 6 by 4. So BP is 6 by 3, BX is 6 by 1. So we just form the matrix and then we'll use our approach of obtaining the elements column by column. So here we also label the rows according to the internal force they are representing. This helps us in easily filling up when we are applying forces one by one on the structure to find out the elements of B matrix. So we have identified BP and BX, and now the next step is that one by one we consider the structure and apply the forces P1 equal to 1, then P2 equal to 1, then P3 equal to 1, and finally X equal to 1. So we'll solve these structures. So here we have the structure, and on this structure we are applying first P1 equal to 1. So it is like a simply supported beam. The top member is behaving like a simply supported beam, and no moment will be transferred on the column because of the presence of the hinge. So we show here the internal forces will be only at one point. The two will be equal to a magnitude of 2.5, but their directions are different, so it's like a sagging bending moment. So when we fill up according to the numbering of the internal forces, we'll have 2.5 and minus 2.5. Because for internal forces we have to go strictly with the sign convention. Then we do the next step, that is apply P2 equal to 1. So this is a moment. So this will give rise to external reactions 1 by 10, 1 by 10 in the vertical direction, and again because of the presence of the hinge there won't be any moment reaction. So now for this case also we can do analysis based on either the left part or the right part, and we'll find that here the two moments, internal moments, are equal to 0.5 and their direction is clockwise. And this can also be ascertained by the fact that at a joint, if we apply an external force or moment, the sum of the internal forces or moments is equal to the externally applied force or moment. So both are equal to minus 0.5 because their sum is equal to minus 1. Then we apply P3 equal to 1. And now the structure is like this. Because we are applying a moment, so the top horizontal member, it is a 2-hinge member, so it only renders the equivalent system like this shown here, that there is a cantilever beam or vertical cantilever, and on the top we are applying a moment and the cantilever is free to undergo horizontal displacement. So the only moment will be in the column. So beam will not carry any moment because now this acts like a 2-hinge member or a link element. Then finally we have to apply x equal to 1. So we can analyze both the parts and we can find out the internal forces at the desired locations by just equilibrium, and the answer we are writing in the form of the components of the B matrix. So this is now Px. So this way we have formed the B matrix also. Now here, what is the compatibility condition? Compatibility condition is that the relative rotation ux, which represents the relative rotation between the two members at the joint, that will be 0 because the joint is a rigid joint. So this is our compatibility condition, and once we use this condition ux equal to 0, we can find out x, and after x we can find out the other remaining unknowns like the displacements and the internal forces. So you can solve this problem, but after the solution we have to superimpose the results of A and B1. So this is a practice problem for you. You are given a similar structure but with a point load. So try to solve this structure also, but now choose a different redundant, maybe some other internal force or some external reaction may be chosen as the redundant. After having studied the matrix force method and comparing it with the direct stiffness approach, we can just do a critical review. Now the first point is that the procedure of the matrix flexibility approach cannot be converted into a general purpose program just like in the case of the direct stiffness approach. In direct stiffness approach, we have a general purpose program, and this program can be used for any structure, and you have been given an assignment also to solve. But in the case of the flexibility approach, we cannot have a general purpose software like that. It can be at the most for a subset only, because here the external forces P1, P2, P3, etc. they go on the overall size of FTS. Next is that here some manual intervention is definitely necessary. Even if we can write a program for a specific set of problems, then manual intervention will be definitely necessary.
Hence, the method is not suitable for automation as in the case of the direct stiffness approach.
So at the end, we have to use manual intervention. Only then we can get the remaining internal forces. But in the case of the stiffness approach, we were getting all the 6 member forces at the end in a compact form. Next shortcoming is that as an intermediate byproduct, we need to form FC. And the formation of FC is very much inefficient from space considerations. FC is very large and most of the terms they are simply 0. Finally, now we see a comparison between the stiffness approach and the flexibility approach in terms of the unknowns. Now in stiffness method, if we consider a member, we can have 6 independent unknowns because they are all displacements. But in the case of a frame member and solving by the flexibility approach, we can have at the most 3 unknowns because there are 3 equilibrium conditions. Hence, this is again rendering. Now we also see the difference between the two methods in terms of the unknowns for a member. Now in a beam member, if we are solving by stiffness approach, we can keep 6 independent unknowns in the form of the 6 displacements, the 2 rotations and 4 forces. But in the case of flexibility approach, because forces are the main unknowns, we can at the most keep 3 unknowns because we have only 3 equilibrium equations. So this is another problem associated with the flexibility method. So because of all these constraints, flexibility approach in the matrix format has not been very much popular in the commercial sector with the practicing engineers. So that's why in this course also we have limited the coverage to basic understanding, and we have not dwelt into more complications, and also we have not touched the programming part. So we have tried to explain the method in conceptual manner only. We in this course have more emphasis on the other topics like the direct stiffness approach, which has practical relevance, and the plastic analysis. So we have deliberately kept limited coverage to the matrix flexibility method. So thank you very much.